get you an impression of the different techniques that are possible to microfabricate some MEMS devices. So I'll start off with some here's an overview. Yeah? So we're going to start off talking about wet etching primarily today, and then we're going to talk about dry etching. So wet etching, of course, has to do something with liquids, whereas dry etching has to do something with gases. And will explain the difference between bulk and surface micromachining. Then we're going to talk a little bit about how you can deposit things on a wafer as usually a thin layer, and usually you don't only deposit. Deposition techniques are sputtering and evaporation primarily. Electrodeposition is electroplating as well. So you don't usually just deposit, but you also pattern then the layers you have deposited. And for that you need the etching again. So it's a kind of a cycle we are going through here. And then I spent probably only a little bit of time on some other fabrication techniques. Focus ion beam milling, laser deposition techniques, but I'll just mention this on the side, so to say. There's of course more than what I can show you in just a few hours we spent together. If you really want to get into this, and you have to come to the clean room and like these guys, and do some hands-on experiments, and then you're busy for like 3-4 years and so on. So I'm doing here etching as well, because I just scratch the surface, so to say. Good. Just to whet your appetite a little bit. So this is a timeline of key MEMS fabrication technologies, and we're gonna start in the 1980s, where people look at structures like this and how to make them. So this is mainly really dependent on alkali etchants, which etch at different rates in the different silicon crystal directions. So basically the silicon crystal planes are being etched at a different speed. So more on that to follow today. What you can do with this, for example, you can make pressure sensors, you can make inject head nozzles. These were the first success stories of MEMS devices, and they are still around, and they are still having a big market share. If you go back to the slides from last year and look at the and last week, if you look at the value of the market there, these are still big shares. Then in the 1990s, people started developing what's called surface micromachining. You see here an important difference, which I'll mention later again because it's important. I'll mention this here maybe very briefly for the first time. This is wet etching, and it's not equivalent to, but it's often has to do with making structures in the bulk of a silicon wafer. So the thickness of this structure originally is a silicon wafer, as we saw last week, and then you chew away, you take material away, and you use the bulk to actually have your structures full. And this here is fundamentally different. So the bulk, the silicon wafer itself, is left untouched. It's still there after your processing, after your fabrication. And you effectively you only use this as a base plate to build things up. And you do this on the surface. On the surface of your silicon wafer, you add structures on layers, but the bulk of your wafer is left as it was. So this is usually called surface micromachining. You machine on the surface, and here you machine in the bulk. So you can make some sort of freestanding structures, and you can probably imagine already if you make a structure like this, there where it's white, between the blue and the gray, there must have been some other layer at some point. We deposited this at some point, and then you removed it in this gap here. Okay? And this layer that has been removed, that's usually referred to as a sacrificial layer, or a sacrificial etch. And that frees then these freestanding structures. So in this case, it's a simple cantilever beam. Of course, you can make much more complicated structures with that, like what you see here, for example. If you slice through here one in one direction, you in the cross section, effectively you get this. So the main companies that develop these techniques, sacrificial etching or surface micromachining, they were US companies, Texas Instruments and Analog Devices. Texas Instruments I mentioned, mentioned already, with the digital light projector which you have in there, these micro mirrors that tilt. They are fabricated with sacrificial etching, surface micromachining techniques. And this here is, well, it's an accelerometer developed by Analog Devices. The motivation to develop this was coming from the automotive industry. Remember the slide, 3 waves of MEMS devices from last week. So this is something you have in your car routinely now and saves your life when you have a crash. This senses the impact and blows up gives the signal to blow up the airbag. So this was 1990s, and then 2000. What you have now here, if you go back here, so you have this nice differentiation of bulk micromachining, surface micromachining, and this here is this is something in between. So you have a wafer here, and you do work somehow in the upper layer, but you also go into the bulk. So it's a kind of a combination. And really key to this sort of development was a process we're going to come to in more detail, that was developed by Bosch, and that's called deep reactive ion etching. And deep reactive ion etching allows you to make very deep, very rectangular, so 90-degree sidewall angles, structures like that, very deep and very nice 90-degree sidewalls, into silicon. So structures like this. So this is from STM, the French, Italian company, Silicon Microelectronics. So, deep bracket line etching, and of course you can use these techniques for all sorts of different things, yeah, so accelerometers, gyroscopes, microphones, and so on. So that was one key development in the fabrication technique. And the other one was the introduction of other materials, which are, yeah, how shall I phrase this, more foreign to silicon. Yeah, so far it's silicon and silicon related materials and maybe a metal. Yeah? So it's silicon dioxide, silicon nitride, and maybe a metal. Yeah? But here you see really the introduction of new materials, for example, piezoelectric material. So aluminium nitride is a piezoelectric material. And if you put a voltage across there, you generate a mechanical stress. And then this membrane you have etched here starts to deform and deflect. And what you can do with that is, for example, make filters, bulk acoustic resonators. So these are effectively mechanical film bulk acoustic resonators, FBARs. These are effectively mechanical filters. And this is, Avago is a very prominent example of a commercial success story. And this is in every mobile phone, effectively, a signal filter. So, and now in 2010s, which we're coming to an end already, the maybe key development here, well, nearly 10 years ago or so, was to actually, if you look at this, well, if you look at the lower part here, that's the same diagram as there, but here you basically add a cap to it, right? And this allows you now to make structures that are hermetically sealed, and you can control the pressure here inside. And in particular of interest is you put a vacuum inside there, right? So you evacuate this. And then you bond, well, you can say you glue, bonding is another word for gluing in a way. You glue two parts together, and there's usually an intermediate layer here of some metal eutectic bonding. So here it's aluminium, germanium, or goldium. These are metal, so they also can form an interconnect, an electrical interconnect. So that was a key development. Allows you to create controlled environment, mainly vacuum in here. Hermetic sealing. And what is key here is the word wafer. So you don't do this at the individual chip level, but you do this at wafer level. So you produce a wafer, 200 millimeter or so, with many devices, hundreds, sometimes thousands, at the lower end. And then you put another wafer on top, wafer level. And in this way you seal all these, let's say 1,000 whatever devices at the same time. So it's a wafer level process. That was the key invention here, or development here. So what you see here is from an American company. Again, they make the gyroscopes for the iPhones, among other things. And let me just finish. I'll come back to you. And they, what they do is they also put here inside the cavity, so here you have a MEMS device, and they put also a CMOS ASIC inside the same cavity and interconnect them inside the same package. Sorry, here is no electronic, so inside the same package. Okay, and in this way you can make resonators. You can make combo sensors, meaning they combine different sensors together, accelerometers, gyroscopes, magnetometers, pressure sensor, and so on. And they're very successful with this. Yeah, please.
So there's two wafers, both of them developed separately, and then
yeah,
they are
processed
together?
separately. Yeah, exactly.
And then it has to be aligned in a
Yes.
way.
Alignment is a good point. Yeah, this is not trivial because silicon is not transparent. Yeah? So you can't look from one side to the other side, yeah? Like on glass. It is transparent in the infrared. So there are infrared cameras with infrared. You see markers, they use alignment markers, and in this way you can align. There was another question.
Yes, with what precision can that be done?
The alignment?
Yes.
Routinely 1 micrometer, and if you work a bit harder, below 1 micrometer, half a micrometer, something like that. There are systems, there are bonding machines that have a camera that looks from the top, and they have an optical path with mirrors and complicated optics that goes around and looks at the bottom. And then you can see you have 2 images basically, and they're being then aligned, or with an infrared. That's the alternative. Then you can look through the silicon. Okay.
I had a question.
Yeah.
This ASIC integration, is it monolithically or?
No. So what's meant here is you have the MEMS with the mechanical structure, and then you have the interface ASIC, the readout on a different chip.
Okay.
But they sit in the same package, so it's also called an SOP, a system in a package.
Okay.
Now there is the possibility to have them on the same chip as well, right? This is technically possible. Analog Devices, for example, does this with their accelerometers.
With the
Right.
what?
With their accelerometers.
Oh, okay. I don't know what.
Yeah.
Accelerometers.
Yeah.
Okay.
Okay. So this is the mechanical part, and I'll come back to this later. I have pictures of this. Around it is CMOS electronics on the same chip. So this is possible. Yeah. And if you now ask me what is better, the answer to that, there is probably no clear answer either way. From a commercial market share, there is maybe 50% fully integrated and 50% what's called a hybrid system. So mechanical structure and the electronics on 2 different or 2 separate chips. Okay, good questions, thanks. Okay, so this is in a way only to whet your appetite, so to say. So fabrication highlights, and now we're gonna go into the nitty gritty, and we start here, and look at that, and next week or maybe the week after we look at that, and so we build up our portfolio of fabrication techniques. Okay, so common to all fabrication techniques is lithography. So this is a key fabrication technique that you require in any process, regardless of what you're doing. And the main steps are shown here. So you have your wafer. So this is the darker lilac, and then you have the photoresist, which you coat you spin coat this is a liquid, and this is an organic substance which is light sensitive. And then you have a mask. So a mask is effectively a glass plate, chrome often. Sorry, a glass plate with chrome as a metal in particular areas where it's dark, which blocks the light. So, and then you come up with a light source. So here should be a light bulb, and you can do this with, for example, UV light, and you can also do this with visible light. Depends on the kind of features you want to have. UV has a shorter wavelength, so you get smaller feature sizes. The MEMS feature size is maybe not so important, but more for the CMOS electronics. So then you expose your photoresist where the mask is transparent, where the light can go through. And then you remove your mask again, and the light does something to your photoresist. Right? It either cross-links, makes it harder, in the areas where it was exposed to light, and then you put it into a developer. A developer is a fluid, acetone in the simplest form, that dissolves this organic photoresist. But it only dissolves it where the mask has been exposed to light, or if you use a different type of photoresist, it's just the inverse. So there are different types of photoresist, positive or negative photoresists, and either where you have light hitting the photoresist, it becomes harder, or just the other way around. So now you get basically a pattern here, which is either this or the inverse of what you have in your photomask. So this is a very crude summary of photolithography. So you come to the spring semester, we spend an entire lecture on this, just photolithography. Some of you were in the class, so you probably know much more about this already. But this is a very crude summary to an extremely complicated process in reality, especially if you make microelectronics. For MEMS, it's not so complicated because typically the feature sizes in MEMS sensors are much larger than in microelectronics. Microelectronics, you go, we are at 7 nanometer now. In MEMS, maybe a micrometer or half a micrometer or so. Okay. So, just very briefly brushing over this. Okay, so here is a cycle of a process step. Right? So here is your wafer. And typically you start by depositing a layer everywhere, blanket deposition. So, I don't know, take as an example silicon dioxide. You grow this, deposit everywhere on your wafer. You may want to modify this by some chemical means, but this is an optional step here. And then, okay, you want to have not only everywhere your layer, your silicon dioxide, you want to pattern this. And for the patterning, well, you need the masks. So you transfer with your photo mask a pattern into your layer by a pattern transfer. No? And a pattern transfer is usually done by some sort of etching process. And you probably will do this several times. So you build up stacks of layers that are patterned in various ways, and etched in various ways. And then you can maybe have a wafer bonding, as I had in the last example on the previous slide, where you bond two wafers together, which has a different pattern and a different etch chemicals and so on. And then you are at the wafer level still, and if you are then doing commercial work, you will do some wafer level testing first, and then you cut your wafer into individual chips. That's the dicing. And then you package and you do a final test, and then you send it to the customer. So we're going to mainly talk about this stuff here. Okay. This is usually called the front end process. This is usually called the back end process. Or sometimes abbreviations are used, back end of the line. Yeah.
As for the wafer bonding cord, is it just to have a vacuum for the packaging? And
No. The vacuum is not to hold the two wafers together.
No. Oh, I mean, like the need to have another wafer with another pattern to put on? Is it just
not only, it's it could be other things. It could be a fluid in there. It could be a nitrogen to prevent reactions taking place. Vacuum is the most commonly used motivation. So it's the most common motivation to do that.
But
not
it's mainly about
exclusive.
the environment of the device itself. It doesn't go into the device.
It doesn't go into the silicon. No? Yeah, it doesn't go in. Usually not inside or of what is inside of the cavity. Yeah. But I mean, if you want to talk about this for a moment longer, then why would you want to have a vacuum? Right? So let's say this is your cavity, like on the previous on the slide, and you have these beams here, and somehow you use a mean to make these beams here move. So they resonate. Let's say. They resonate like this. So let's say it's a gyroscope. Maybe we'll come back to gyroscopes at the very end, but without going into details what a gyroscope is, let's say they need to vibrate. This middle thing here needs to vibrate. So I want to have here vacuum. Why? Any idea?
To make it easier.
Make it easier what?
To reduce damping.
Lower pressure.
Yeah.
low
So
pressure.
yeah.
The
Low
vibration.
pressure?
The vibration.
Yeah. Damping is the key. Yeah. So if you do this in air, so without a cap, then I get. You're familiar with the concept of the Q factor, quality factor. Yeah. So let's say this is a typical gyroscope design. This is maybe I didn't say how big it is, but let's say it's about the size of my hair, of your hair or my hair, 50 micro, 100 micrometers or something like that. Yeah? So if you do this in air, and I vibrate this, what kind of Q factor do I get in air? What do you guess? Numbers. Go on. 100?
No.
Perfect. Yeah? Around 100. Yeah? If I do this in vacuum, what do I get then? Orders of magnitude bigger. Yes? How many? Give me a number.
10,000.
Okay? At least. Yeah? You can go up to 1 million. Yeah? Depending on the design and other things. Yeah? So you get a much better resonator. Yeah? And that's a key for many applications, sensing applications, gyroscopes, gravimetric sensing, and so on. Yeah? That's the main motivation why you want to have vacuum there. Okay? Right. If you go around this circle a few times, then you might end up with something like this. All right? So here you have a stack of different these loops. Deposition patterning with a photo mask going around. And this is not just drawn randomly, but this is a commercial process as well, where you basically have what is not shown is the silicon wafer. So here sits the silicon wafer, right? That's the substrate, my building table where I build things up on. And then I have a very thin layer of nitride. So it says nitride here, but it actually means silicon nitride. Yeah? And then I have a thin layer of polyzero. Any idea what that means? Polysilicon, yeah. Yeah.
Different orientation.
Yeah. So it's chemically the same element, yeah, but it's a polycrystalline silicon, form of silicon. Yeah? So it's not perfect crystal as in your wafer, which is not shown here, but it has these grains and they are orientated in a random way. Thin layer, then we have where it says oxide. You see it? This was obviously let me go back to the polysilicon. The polysilicon was first deposited everywhere, and then you use this mask lithography to obviously remove it here. And it's gone. Yeah? And same with the silicon oxide, silicon dioxide. To be more precise, silicon dioxide was deposited everywhere. But obviously, it was etched away here and there. Photo mask, lithography, etching away in these locations. And then you have another layer of polysilicon here. Also, it was deposited everywhere, but it was etched away here, everywhere, except for here. Then you have another layer of silicon oxide, here, same thing. Another layer of polysilicon, and then eventually you have some metal to make some electrical interconnects. Yeah? So this is a US foundry process where you can, if you want to as a PhD student, you can send designs to and they fabricate this for you. And then after a few months you get things back like this and you can release some structures and so on. Yeah? So it's quite a famous MEMS process. But the point here actually is, if you do this, after a while, your surface is not flat anymore. Now, of course, this is not to scale. This is grossly exaggerated how thick these layers are. Well, to put some typical numbers to it, what do you think? How thick is this oxide layer here, for example?
100 millimeter.
Sorry?
200 millimeter.
No, that's a bit thin. You think you're microelectronics.
2 to 3 micrometers.
Yeah, 1-2 micrometers, something like that, right? And in this particular example here, yeah, the polysilicon layers, these green and the gray, they are also of this kind of thickness. Okay. So, and yeah, put this into perspective. So this is 2 micrometers. This is 2 micrometers. This is a bit thinner here. This second oxide layer. Put this into perspective to the wafer thickness. Yeah? The wafer is not shown, as I said here. So the wafer, typical wafer thickness, I didn't say. Well, it's a thin wafer. 500, yeah? So 400 or 500 micrometers. Depends on the size. If you go bigger, then it also gets a bit thicker. So it can go up to a millimeter or something. So you're using here a couple of micrometers at the surface. So this is a typical example of a surface micromachining process. Okay. Right. Let's go wet. Let's go into liquids. Yeah. So we have etching. I have 2 options, wet and dry. So this is the wet. So what's happening here is, well, I have here my silicon, and I have here deposited a mask layer, and I have patterned the mask layer. So I made openings here somewhere. Here I made 1 opening. Of course, on a wafer scale, you make here millions of openings. Yeah. And then I put this into a bath. Usually there's some acid in there. And after a while I take it out. Right? And then I get something like that. So what I didn't say here is actually I have here an intermediate layer. I have this dark gray and this is my silicon. Right? So the acid has etched away here this dark gray layer. Now ideally, you see already it was not ideal. Ideally I would like to have exactly here a continuation of the side wall into my dark gray layer. But things are not ideal. So etching occurs down but also sideways. So this leads to undercutting. So here you have some undercutting going on. And usually, not always, but usually this is something that you want to avoid. You don't want to have this. Not always. Okay, so this is wet, obviously, because I put it in a bath. And then I have dry etching. Often this is done with the help of a plasma. So in the gas phase. So here I have also a mask layer, masking layer. And I don't have this dark gray because I do something else here. It's just an example here. And I put this into a plasma etching device, machine. This is my wafer. There I have, well, usually I have vacuum in there, and then I introduce a little bit of the source gas. So the pressure in here is usually very low. So there's no air in there. There's only a bit of etching gas in there. And then I activate this gas because I pump some energy in it. You often done with an RF signal, and this makes a plasma. in there, and the plasma consists of an reactive gas, and this reactive gas then etches away into, in this case, into my silicon. Right? And I've got an exhaust here as well. Okay, so that's in a nutshell dry etching. So we're going to talk now about wet etching a bit more. So, sorry, before we come to that, here's another slide on that. Wet and dry etching is the one important characteristic. You can differentiate the processing. And the other one is isotropic and anisotropic. So some of you will know this. Some of you will not know this. Isotropic effectively is the same speed in all directions of the etching. And anisotropic means somehow I have a directional dependency of the etch speed. Okay. If I look at the wet etching, isotropic, the features you get are dependent on the mask. If I am in an anisotropic case, it will also depend on the crystal orientation if I want to etch silicon. Most of the time we want to etch here silicon. So this makes things complicated. Silicon is a complicated crystal. If you turn it and so on, it's not so easy to imagine what's going on there. So crystal dependency. The dry etching usually is only dependent on the mask. So whether you're doing isotropic or anisotropic etching, the mask determines your features. And to give you examples, so isotropic wet etching, it gives you a sort of a circular structure. So if it's completely isotropic, it should be a perfect circle. But usually it's not completely isotropic. So it's isotropic is an ideal case. So, then we have anisotropic, that gives you, depending on the crystal orientation, gives you slanted sidewalls. And these sidewalls, they are determined by a certain plane, which is the 1-1-1 plane. Meaning that this 1-1-1 plane etches much slower than other etching planes. Dry etching, well, isotropic, almost isotropic. It's distorted circle, and it's probably more distorted than here. And then mask dependent, you can make almost these 90 degrees. This is also idealized. It's not really so nicely, but close to that. Yeah.
What can we use for in order to do dry isotropic etching?
Dry isotropic, well, it depends on what chemical you use and to etch what kind of material.
Okay, for silicon.
For silicon, xenon difluoride is an isotropic silicon etchant, for example. Yeah. There's also a chlorine molecule or chemical that also etches silicon isotropically. Here, okay, yeah. Okay, so I'm going to go a bit faster now, yeah. Etching is is a complicated process depending on many parameters. And here I only have the most important ones listed. Of course, the chemical composition, the temperature, whether you stir or agitate, mainly in the wet phase. Yeah? If you put a spoon in and nicely stir, you're going to get different results as if you don't do this. Of course, the time, yeah. Of course, the doping concentration of the material, and sometimes also additives you put into the material. So here's for wet etching. Yeah, so this is pretty much a ideal isotropic profile. Here's an opening in your mask layer, and whenever fluid goes here, it etches in all directions at the same speed. Now, of course, what kind of opening, how big this is, depends on how big your initial opening of your masking layer is. This is a perfect idealized picture with a lot of agitation. And this is basically if you don't stir in your bath. Then you get more something like this. Why? Any idea?
Etching is direction dependent?
No, you use a chemical that actually etches silicon at the same speed in all directions.
Yes, using the agitation or stirring would make the liquid, if it's quick etching, the liquid would have more access to more parts of the
It
silicon.
will remove the etched substance from the
as
bottom.
long as you keep vibrating.
Yeah.
It wouldn't have the same concentration.
Yes. Yeah, good. Yeah. So that the local concentration, if you just let it sit there, the solution, you will have a bit of convection because it's at a certain temperature, but there's not much mass transport of the etching solution away from where the etching is taking place and away to other places. So that's one of the main reasons. So locally the concentration then drops. Whereas here you really stir, concentration is uniform, which is difficult to achieve through such a small opening here, of course. So it's an idealized picture. Okay, isotropic, anisotropic. Now this is a different chemical, of course. So here wet etching would be HNO and HNA. I come back to that later. But here you have then a crystal dependent etch speed. That would be KOH, which again I come back to later. So here you get a clear slanted profile, which is typical for an alkali wet etching process. And this now depends on the crystal orientation, and the usual 99% of all wafers, silicon wafers, are 100 wafers. So the top surface is a 100 wafer, but you can also commercially buy 110 wafers, also 111 wafers, also commercially available. And then if you put this into the same chemical with the same mask structure, you get totally different results here. Okay. So here are a couple of examples. Nice isotropic wet etching profile. Things like that you can also do. You see here this slope around it. And there obviously was another one rounded here, and if you make the masks so that they overlap a little bit, then you get a very sharp tip here. And with this you can make micro needles, for example, with that are really sharp. So if you zoom in with an SEM here, the radius here is almost atomically sharp. You can, if you have something like that, if you change the agitation a little bit, so this is a sort of a rounded structure here, and it's the window, and here you see the stars. That was a joke. So this is a channel into silicon. And then what you can do is here this lighter gray structure. This is silicon dioxide. So you first have etched the silicon with isotropic, well, almost isotropic. It's not. It's a sort of a deformed circle again. And then you oxidize the silicon surface, and you can re-seal this opening. So you can make a channel into looking into the board. So you can make channels and you can seal them again, and now you can have some liquids flowing through there, or some gas or whatever, or some medical substances being pumped through here, or something like that.
How is it possible to see them now?
Well, because you have a growth here of the silicon oxide. So there's silicon, and this starts growing, and it grows in this direction and grows in that direction. And then, so silicon dioxide grows on silicon, and if you do this long enough, it closes this opening here. This is only, what is it here, 5 micrometers, so it might be 10 micrometers. This takes a while, but it's a growth process. So effectively, what you do is you put it in an oven, and you have a precursor for silicon dioxide, silane, for example, and then you can seal channels like this.
Wouldn't that be dangerous? I mean, like, it would seal the channel itself?
Yeah, but that's in this particular example, this is the, you mean the entire
I mean,
channel?
it
Yeah.
can go everywhere. Right?
Yeah. Okay. Here what you have is a slower oxide growth rate than there. Why? Here it's a much higher concentration, and this is a wet growth process. Right? So here you have much higher concentration of your precursor than in here. And therefore the growth rate here is much faster. So at the beginning it's the same, but after a while the growth rate here becomes much faster than inside here, because your precursors can't get into this partially filled channel anymore. It requires a lot of process optimization. It's not something that you do on a Friday afternoon or so. But in a nutshell, this is what's going on there. So these are just a few examples what you can do with this. This is a little bit of an unusual looking figure. So this I've shown you last week already. Typical 100 wafer, and it's put here in a coordinate system where you have the 3 main axes. And so if you put this now into a KOH solution, you will etch this shape here. And the side walls, these slanted side walls, they are all made of 111 planes. So 111 planes, they etch much slower. So this side wall here, this side wall there, and this side wall there, they're all 111 planes. And the black part there, this is a 100. So why is this still there?
Why? Like, why is it still there?
Why is it still there?
The directionality of the
They interrupted the etching.
direction is
They
Yeah,
interrupted.
yeah, but by the etching etches the 100 faster. Right, there's somebody at the back, somebody else. Come on. Come on.
Why is the paint still there?
Yeah.
Because they stopped
Yeah, but why?
because they wanted to have a. So
Yeah, but how did they stop it?
They just take it out from the solution.
Okay. Just take it out of the solution. That's the simplest one. I look at my watch and say, okay, now I'm finished. I'll take it out. Okay, I can do that. Yeah.
You can calculate.
That's a timed
Etching.
edge stop. Yeah. There are other ways, and I'll show you this a bit later, next week probably. Yeah. If you change the doping in here, it will also stop. Right? So this timed etching is possible, but it's not very precise. Okay? So meaning that if you repeat this, you do this on a Friday afternoon and you get here a remaining membrane of, I don't know, 10 micrometers, and then you do it on Monday morning again when you come back to your lab, and then you do exactly the same thing. You think you do exactly the same thing, but suddenly the membrane is, I don't know, 12 micrometers. And so the variation is of this timing is relatively high. Yeah. Yeah. Okay. These are the 111 crystal plates, and they come out. So they are the planes that etch the slowest. Was another question?
Yes.
Yeah.
So the more precise way to create weighted channels would be using the dopant technique.
There's doping, and there is an electrochemical etch stop where you bias your wafer from the back against the reference electrode, and then you also can stop. But I have some slides on this later.
Okay.
Yeah? Now, what's going on with the chemistry? Very briefly, yeah. So I have here a 100 substrate. Now, on a 100 substrate, at the surface, I have silicon atoms. These silicon atoms, remember last week, silicon atoms, they always want to have 3 partners. Sorry, 4 partners. 4 partners, because there are 4 valence electrons, but they want to always pair with 4 others. But the silicon atoms sitting at the surface of a 100 plane, they can only pair with 2 of the crystal, in your crystal orientation. So they don't move about. The silicon atoms, they're fixed in the crystal. If you look at the surface of a 100, the surface atom only has 2 partners. And he doesn't like this. And that means it can be removed relatively easily. So the energy required in the chemical etch, it's the Gibbs free energy required to remove a silicon atom of a 100 plane is relatively low compared to a 111 plane. And the chemical reaction, what's going on there? So first of all, silicon has these additional, it would like to bond with other pairs, but it hasn't got one, so it takes OH minus from the liquid, from the water effectively, hydroxyl ions that are always there in a watery solution. So it binds with 2 hydroxyl ions, the surface ones here, and then the etching comes along, and what happens now is this bound by this compound, SiO2, double negatively charged, yeah, with two additional hydroxyl ions that are floating in here, forms this compound, and that is a chemically relatively stable compound. And this goes into solution. So it kind of floats away. So from the energy, it's advantageous to form this SiOH4, and of course, to balance the equation, it releases 4 electrons. And the last reaction that's also taking place is that, well, with these electrons here, the water gets reduced and forms again OH minus. And so the cycle is complete, so to say. Yeah? And the OH minus, in this last reaction here, what's happening there is you create a gas, hydrogen. So you create hydrogen, H2, and that's a gas. So you get some bubbles. Your bubbles coming out of your bottle. These bubbles, they can be very problematic, because if you now suddenly have a bubble here hanging of hydrogen, they tend to stick to the surface also a little bit. Friction forces at the surface, van der Waals forces and stuff like that. And then your etchant can't reach to the surface here. Yeah. So you get a sort of a micro masking effect if you have a big bubble hanging there. Right? So that's a problem. These hydrogen generation. So this is the story for 100. If I look at now the other planes, they have at the surface different structure. So here, 100, only two partners, so to say, for one silicon atom that's at the surface. If I have 111, the silicon at the surface, the atoms at the surface, they have still 3 partners. So they only can at most bond with 1 OH minus. And then this reaction doesn't take place, what I showed on the previous slide. With 110, it's sort of in between. You also have 3 partners for each surface silicon atom, but the other 2 of the other 3 partners, they are also surface atoms. So it's not as strong as that, but not as weak as this case. So it's in between. And to visualize this further, so this is a fairly nice view graph to show the surface structure on 111, 100, and 110. And what you basically see here is that the 111 is the most densely packed surface structure of silicon from the crystal orientation. And the 100, the most loosely packed, and the 110 is in between. So you can sort of intuitively visualize and understand that this here, it's much more difficult to remove a silicon atom from the surface as here, just from the packing density. Or surface density of the atoms. Okay, now I've got a couple of tables. we have here wet etching. Let's look at this first here. So this is a etchant solution, a combination of 3 chemicals, HF, hydrogen fluoride, HNO3, and then a buffer. That can be either water or this here is vinegar. Yeah, it's a weak acid. And this is usually abbreviated as HNA, and that is a relatively good isotropic wet etchant for silicon. These rounded channels and so on, what I showed you before, that has been made with this combination. Yeah.
According to the slide, I need to etch, so I need to have higher concentration of OH.
Yeah,
So
and this
I,
is
so
yeah.
I need an alkaline solution.
Yeah,
not
the KOH.
bases or acids. So acids will lower the OH and increase the etch.
Yeah, wait a minute.
I mean,
That's
okay.
that is
Yeah,
isotropic etching. When I talked on the previous slide, this is anisotropic etching.
Okay.
So yeah, sorry, maybe yeah, I understand what you're saying. So this is what's going on in KOH. Right? Yeah, I should put this on the slide actually. Yeah? So the KOH, you put KOH there. It's an alkaline solution. The K, potassium doesn't play a role. But the KOH, it's the OH minus that is doing the etching. I didn't say that. Yeah, sorry. Okay. So, but what I'm doing here in this table, I go back now to isotropic etching of silicon. And what you have here is this combination of these 3 compounds at different concentrations. Yeah? So you can now mix these 3 etchants, and then you get etch rates in the order of a couple of micrometers per minute. Here it's higher depending on the mixing. Yeah? This is isotropic. So what here you have the etch rate ratio. Huh? So this is the ratio of the 100 plane to the 111 plane speed of the etching. Huh? And for this chemical, HNA, there's no difference. So this is an isotropic etching of silicon. Huh? It has some sort of dependency on doping, yeah, but not very strong. Let's not talk about this too much. What kind of mask layers can I use for this? I can use silicon oxide or silicon nitride. This is silicon nitride. So this is isotropic etching. Yeah.
The doping, what do you do? I don't understand. The doping part.
So doping, if you have silicon, often you dope it. You know what I mean?
Yeah, I mean here. So it depends on the dopant.
Yes, it depends on the doping. So what we have here is if you have low doping, 10 to the minus 7, 10 to the 7 per centimeter, yeah, is a relatively low doping concentration of boron, of phosphorus, of arsenic also. Yeah? And then the etch rate goes down. So this is decreasing.
So how is it like the H rate is from 0.7 to 3, but it would be diminished by 150? Is it like the numbers?
Oh yeah, there's a number there.
Is it 150 micrometers per minute or what is it?
No.
Is it the ratio?
Maybe like a factor.
Factor divided by.
I have to double check to be honest, I don't know. It goes down, but I can't, yeah. This is from a textbook, this table. I need to double check. I don't know the answer. Yeah, please.
So for the doping, it doesn't matter whether it is N or P type.
Not much, no. There's not. I mean, if you look at this here, at this combination of these three chemicals together, you basically have no dependency on the dopants. Yeah? And here you have a slight decrease, but I have to look up what. Just delete this 150 for the moment from your notes. Yeah. So I have to. I can ask my PhD students to look this up for me. So next week you explain this. Yeah? Okay. It's also dependent on the temperature. These etching processes are strongly temperature dependent as well. Okay, so this is isotropic, yeah? And this is now anisotropic. Why is this anisotropic? Well, if you look at this column here, yeah, you have a ratio of the speed, yeah, where the 100 etches, in this case, 35 times faster, and in this case, 400 times faster than the 111 plates. Yeah? Now, these ratios here, it's never infinity. Yeah? So it means that the 111 planes also etch, but much slower. Yeah? So don't say they don't etch. They do etch, but at a much slower rate. Yeah? And KOH we have already talked about, so mainly the donor of the OH minus. Temperature usually a bit higher, etch rate in the order of 10 to the minus 4, and here you have silicon nitride, silicon oxide as masks. Then you have another etch solution, EDP. Yeah, so it's this chemical here, and it's always buffered. It's buffered in water or in IPA, alcohol, effectively, and so on. And I have to also look up this. Oh yeah, wait, it does make sense now. So actually, here KOH. This is the etch stop. So if I have highly doped silicon with boron, then the etch rate goes down by a factor of 20, or here for EDP by a factor of 50. Yeah? And for HNA, here if you have a low doping rate, it goes really down to almost nothing. Yeah. So it's really a reduction by a factor of 150 here for HNA. If you had asked me now this, I wouldn't have known this either. So it's, if I don't know it, it's not so important. Yeah. Go on.
So basically, you would need doping in order to have a higher rate in the first place.
Yeah. Exactly.
And stop it
Yeah.
and
Yeah. Well, here you can stop it. This is what's used as etch stop.
I put tubing.
It will be a reverse for others.
Yeah.
Yeah. I mean, it works the exact opposite way when I'm using isotropic agent, right?
Yeah, exactly. Yeah. It's just the other way around. Yeah.
So this means that with the first compound of etching, you do etch your 10011 planes at the same rate. So
This is an isotropic etching. Yeah. So this is really isotropic. Yeah. So meaning there's no speed different, etch rate different between 100 and 111. Huh? So isotropic, anisotropic. And you see it by this ratio. Yeah?
How thick does the mask has to be?
Sorry?
How thick does the mask have
How
to be?
thick is thick, yeah. usually it depends on the depth,
Mhm.
because also these solutions do etch the mask. And I think I have it in a follow-up slide somewhere, but it's usually in the order of maybe a half a micrometer to a micrometer for oxide, and silicon nitride usually is thinner, 100 nanometers, few hundred nanometers, something like that.
Professor? So in case of isotropic etching, where we use acids, so in that case you won't have hydrogen gas formation, right?
For which case? For
In case of acidic solutions.
for here?
Yeah.
No, there's no hydrogen generation there.
Yeah, so you won't have that micromasking effect.
Yes, correct.
And in case of alkaline, where you have that thing, is there a possibility that the dangling bonds can also be passivated by hydrogen and not OH?
You can add some surface surfactants to suppress this, yes.
Okay.
Okay?
Yeah.
Okay. Yeah, so we talked about KOH, we talked about EDP. There's another one called TMAH. That's another table here. Yeah, here actually is the answer actually to your question about the mask thickness. So depends on the chemical first of all. So KOH selectivity silicon to silicon dioxide is about 200 to 1. So if you want to now etch an entire wafer through 500 micrometers, and you can calculate my mask will also etch, but 200 times slower. And silicon nitride is always better. So here you have 2000 to 1. TMAH is, well, you look at the values here. The most commonly used one is KOH. Right? It's the most commonly used one for fabrication. And yet another table. I think I skipped this in the interest of time. Here you have again these right here. First of all, there are 4 actions mentioned. Hydrogen. This is not really used so much anymore. Here you have the etch rate for silicon dioxide, so nanometers per hour, and the ratios of the different planes as well. Okay. And yeah, last table here. KOH is the most commonly used one, but it has a severe difference. If you go into IMEC and you use KOH, you're immediately fired. Because it will screw up the entire clean room. So it's not compatible with CMOS fabrication. This is why we have people in our clean room coming from IMEC and say, can you just etch something for me? KOH. Because we have a clean room at Karl Löwen, but we don't do CMOS. We don't do circuits. So we have KOH in our clean room. TMAH, here's the abbreviation, is the only CMOS compatible wet etching solution. So that's something, if you use this in IMEC, you probably are being frowned on, but not fired immediately. So it's almost CMOS compatible, I would say. These here are not used very much anymore because they are really nasty chemicals. So, For example, we don't use these EDP and hydrogen. We use KOH mainly and sometimes TMAH. Yeah.
Is it not compatible because of the hydrogen production?
There is, I think, it's more the calio, the potassium, like the K, the KOH, the potassium, because that diffuses into silicon. On a modern CMOS transistor, it can be a single atom somewhere going in the wrong direction, then your transistor doesn't work anymore. The hydrogen is a good question. Actually, it could also be, because of course it's a very small molecule, so it also diffuses into silicon. But I think it's more the potassium actually. You have to do a chemistry course here. Okay, so here you have the reaction again. That's the same as what I had on the previous slide. Okay, let's look more at the applications again. Yeah, so this is typical what you get, and here is a number which you should remember. The angle between the horizontal, so the 1, 0, 0, and the 1, 1, 1 plane is 54.74 degrees. Okay? That's a number every MEMS designer or engineer will know. Yeah? And this black, solid black here, this is your etch mask, yeah? So the silicon nitride or silicon dioxide. Of course, if you have now a big opening, you etch down, and if you don't take it out or you don't use this etch stop technique, it will go actually all the way through the wafer, and you have a hole. You can do that. You can make, for example, micro nozzles or inkjet head printer nozzles in this way. And sometimes you only want to have this, and then you have a smaller mask opening, like here. Yeah, and here, okay, this third dimension is not shown. This would be a channel. So here is an animation of how this etches over time. This has stopped, right? Because it's self-terminating. So once you have this pyramid, inverted pyramid, it stops because you only have 1, 1, 1. Right, it stops almost, yeah? Not 100%. Yeah? This one also has stopped. So this is a channel. Yeah? So if you imagine coming towards you and into the board. Yeah? So you have this sort of channel, and this one would etch further until you're all the way through. Yeah? So it depends on the size and the shape of your mask, of course. Yeah? So if you go further, then you have a hole. Yeah, this is a reminder. If you want to calculate this 54.7, this is how you do it. You can figure this out yourself. And put the numbers in here. This is the procedure. With the milliamperes and so on. Huh? Now you can do this, of course, also from two sides. Yeah. So here you have a wafer. I have a masking layer on the front, and I have also a masking layer at the back. And now I can really do fancy stuff in a way. Yeah? I can do making things like that. I can make membranes. I can make channels from both sides, and so on. Yeah? So here, this is of course an interesting feature because it allows me to make something like that, right? And this is a nice spring, spring, accordion or something like that. So I can make something that is compliant, mechanically compliant in plane. I can make a spring here. It's, I don't know of any commercial application that does that, but there are many papers of academic work that has tried this. Another, yeah.
In the previous slide,
Yeah.
So for this spring structure, how stable is this? So
How stable is stable?
the thickness will be very small and you
Yeah,
will have lots of
but the
stresses.
thickness you can control. You can control this by your masking and the process and this edge stop and all sort of things. It's to some extent surprisingly stable if you use it in the right way. Yeah? So, meaning, well, I said it's a bit similar to what I said last week. It's if you use it the right way, it will last forever. But if you touch it, it's going to break immediately. Yeah? So it's a difficult question how mechanically stable these things are.
So it would depend on the direction of the force.
It depends on the direction of the force. It depends on the direction or on the area. Surface forces can be a problem. But if you really wanted to own these resonators, they resonate forever. And you can drop these things. I can drop my phone. My gyroscope is not going to break. My screen is going to break. So I'm generalizing here. This particular structure, this is not going to be more or less stable than something like this. In general. But
macroscope, it's a different thing. At micro level, it's a different.
Absolutely right. Yeah. But don't forget, silicon is stronger than steel and lighter than aluminium. So it's relatively stable, but it's a difficult question to answer because it depends really on the loading and the way you stress the material. Okay, now, so we talked now so far about the etching of the 100 and the 111 planes. Now, of course, there are many other planes. So you have, I don't know, a 200 plane or so. And what's the etch rates in other directions of your silicon crystal? And this has been investigated by diagrams like this. So this shows only a quarter circle. Here you have, this is the direction of a 111, the 111 direction. This is the direction of 100. And now you have all sorts of other crystal direction or lattice directions, Miller indices, higher numbers, at any angle. And you can investigate this now. And then you get this Easter bunny shape here, with two ears. So what it means is, well, we said this 100 is etching much faster than the 111, yes, but actually there are other directions here, around there, that etch even faster, much faster. Okay, but what it does show is the 111. There it's very small. It's not 0, but it's very small. Yeah, you can. Well, actually, in a way, I've got the wrong order here a little bit. Yeah, you can make these inverted pyramids with openings or not openings. In silicon. This is a complicated diagram. You have to stare at this for like 10 minutes, and it starts to make sense. Right? So you have these inclined planes here, yeah, where effectively this plane here is a 111 plane, and here this plane as well. Right? So these are the side planes of this inverted pyramid. So another effect is the following. Okay, so we have so far said, well, okay, I make a square mask opening. Yeah, so this is the mask. This is your silicon nitride, let's say. This is the opening in your mask, and you put it in the KOH. Then you will get a nice inverted pyramid. But what about if I say, okay, I make a mask opening that's round? I can also do that. And if I do that, surprise, surprise, I don't get a round structure, but after a bit of time, I get also an inverted pyramid. Yeah? And the outer square is encompassing the circle. Yeah? So it starts off with a square, with a round shape, but then it starts revealing very quickly these 111 planes again. Okay. Yeah. This is what MEMS engineer understand under fun. Okay. I'm also a MEMS engineer. I can also think of other things that are funny. Anyway, it's just a nice picture, and here's my wrong order. So here, if I go back 2 slides, or 2 slides. So this here is experimental data, and it comes actually from that. And this is what's called a wagon wheel method. So effectively what you do is you make a mask where you have these spokes of, well, either silicon dioxide or silicon nitride masks, and they go radially outside and go inside to a center point where the resolution is not sufficiently good anymore to show these, to distinguish between one ridge and the next ridge, or opening in the mask. So ignore this middle part here, and then you put it into KOH, and then you get this rather nice looking structure. And then effectively what you see here is the bunny shape again, from the diagram I had 2-3 slides ago. So in this way you can determine the edge rates in all sorts of directions. So this would be here again the 111 direction. And that would be the 100. So the difference here is larger than in the drawing a couple of slides before. In edge rates. Yeah.
I don't get how we change the direction of the wafer in this way. I mean the bottom part here in the other drawing, that's all 100. The wafer is 100.
This here, yes. Huh?
Okay.
This here, yes.
This is the one being etched.
Huh?
And this is the one being etched.
But the side walls are having different directions, and this is why they have been etched at different.
From the side.
Yeah. So you have here, the way this is measured is they shine a laser and they look at the reflection here. Yeah. Now, what you can also do with wet etching is the following. If you make a mask like this, right? What happens then? Now here there's something interesting. You have the concept of convex and concave corners. Right? So inner lying and outer lying corners. And these corners are different to those corners here. All those corners. So what's happening here? Well, let's have a look. After a bit of time, and let's say I do simple etch control by taking the wafer out, I will get this structure. So here I have a concave corner and here I have a convex corner. So with an inner lying and an outer lying corner. Now, if I continue etching now, what happens then? I will get here some undercut. And here at this corner, suddenly higher order planes are appearing. Like in this example, a 411. But it doesn't matter which one it is exactly. Because if you go back to wagon wheel, all these directions here, they etch very fast. Okay? So it doesn't matter whether it's exactly a 411 or a 311 or something like that. That's not important. But it's a higher order plane and they tend to etch very fast. They only appear at the convex corners, not at the concave corners. There I have my nice orderly 111 plates. So as soon as these planes appear, they will etch very fast, and effectively they eat away everything underneath my springboard here. Good. And now I have made a little swimming pool with a nice springboard, suspended beam. And of course this is not silicon, this is silicon dioxide or silicon nitride, so different materials, my masking material. But I can use this now to do maybe some resonator, for example. Or I can deposit something here, or I can make a tip here, and I have a tip for an AFM, I can scan over a surface or whatever. So many applications here. Okay. So with this I can make also suspended beams, not in silicon, but in a masking layer. And then I can also do crazy shapes in my masking layer. So I have here, well, this is my pyramid, inverted pyramid. This is my channel that is self-limiting. And what happens here? What happens there? So here I have my square, but I've rotated this a little bit. What I didn't say so far is that here the edges are aligned along the 110 direction. For this to work so nicely as I explained before. And what happens here? Okay, let's see. So this is what I get. So everything fine here, everything as expected there. If my rectangle is a little bit tilted, I will get the same structure as there, but you see what is being etched is being circumventing the original mask outline. Okay.
It's just over etched.
Well, it's a kind of over etching, yeah. But the point is, let's say you have of your mask making, you always have a tolerance by I don't know, half a degree or something like that. So you will always get a little bit more than what you've asked for. Or you can deliberately do this as well. In some cases you can deliberately do this. But for example, also this here, this crazy shape will come out as a pit, 111 sidewalls, yeah? And in this way, it does not, the point in a way is it does not reproduce this shape here. Of the mask.
Depends on the shape.
It's almost independent of the shape.
Always get the same thing.
Well, you always, if you do this, you get etched this here.
Okay, so why do I make a mask?
Because you could say, I want to have this shape, and you can try it. Now, you would not do this, that's the point. So, I had this on one of the earlier slides, beginning of the lecture. The anisotropic etching is dependent mainly on the crystal orientation, not so much on the shape of your mask.
So the plus shape and the square, they both give the inverted pyramid,
Yeah.
no matter what.
Yeah. Yeah. If you wait long enough, if you very briefly dip this in, then of course you get still your square, well your plastic. Sorry. Yeah. But if you wait long enough, you get here the same as here. So this would give you the same.
Okay, so does this mean that we only have like two shapes, two options? To,
You have little options, yeah. Yeah, you have from your shapes little options. Maybe this is the reason why wet etching for modern MEMS devices is not used so much anymore, because it is limiting in the shapes. Okay.
Is it possible to compensate for this in
Yeah.
your mask already?
There are compensation techniques, and people have published extensively on this. I can't remember quite where I have it, but we are running out of time. So I will show you this next time. Yeah. So here, just to round up a few pictures of actual devices, yeah, so that you believe me as well. So here you have a thin membrane. This is a square membrane, and this is used for a pressure sensor, for example. Yeah. Now, this is the ideal case. This is also dependent quite a bit on the concentration of your etchant of KOH, for example. So this is ideal, process optimized, and then if you lower the concentration, you get things like that. And this is exactly this micro pitting or micro pyramids, where you have micro masking from this hydrogen gas that I mentioned earlier. And if you do things wrong, well, you get that, and if you do it very wrong, you get things like that. Right? So just examples here, what can go wrong. Yeah. Yeah. So this is also an issue. Yeah. Okay, let's break here. It didn't quite come as long as I wanted, but you asked interesting questions, so that's, I think, better than talking about a lot of things. So, have a good weekend. See you next week.